I want you to do something for me right now. Just take a second, wherever you are, and place your hand flat against the center of your chest.
Just right there over the breastbone.
Yeah, and if you wait a moment, you can feel it, that steady, rhythmic thump.
It's always there.
Right. And what you are feeling is a muscle that's roughly the size of your clenched fist, and it has been beating since before you were even born.
Which is just wild to think about.
It really is. And if you are like most people, you probably have absolutely no idea how much physical force that tiny engine is generating just to keep you sitting upright right now.
Oh, for sure. We completely take it for granted.
Exactly. So today, we are doing a deep dive into the mechanics of the human heart and the circulatory system.
Yes, we are tearing down the whole engine today.
We're going to unpack how this relentless biological machine actually keeps you alive. We're going to, demystify its architecture, and we're going to look at what is literally happening under the hood when the plumbing breaks down.
It really is profound when you stop to actually feel it, like you said. I mean, that little muscle hasn't taken a single day off.
Not one.
And the sheer scale of the workload it handles it's staggering. When you run the numbers on this, you are looking at a system that executes roughly 100,000 beats every single day.
Okay, let's unpack this. Because 100,000 beats a day, that means over an average lifetime, we were looking at more than 2.5 billion beats.
2.5 billion without stopping.
2.5 billion. And with every single one of those flexes, it is generating enough pressure to push fluid through a plumbing network that is so incredibly vast, it genuinely defies logic.
It sounds like science fiction.
Right. If you were to somehow take all of your blood vessels out and lay them end to end, they would stretch for about 100,000 kilometers.
Yeah, and to put that physical distance in perspective, that is enough piping to circle the entire Earth twice over.
Twice. Inside of one person.
Tucked entirely inside of you. And fluid doesn't just move through pipes on its own, It requires immense continuous pressure to overcome the friction of all those miles of biological tubing.
Because it has to reach everywhere, right?
Exactly. Every single cell in your body needs a constant, unbroken supply of oxygen and nutrients to survive. And they are constantly generating waste products that need to be carried away.
Right. So the heart is simply the engine creating that pressure. But when I was looking at the anatomy of it in our sources, I kept thinking about the physics.
How so?
Well, if it's just pushing fluid in a massive circle, why is the architecture so complicated? It's not just one big pump sitting in the middle of our chest.
No, it's not. And this raises an important question. Why would one single pump not be enough?
Right.
It comes down to the destinations.
Right.
Blood needs to pick up oxygen from your lungs, and then it needs to deliver that oxygen to your toes, your brain, your stomach.
Which are very different distances.
Exactly. Because those are two entirely different jobs requiring two very different amounts of force, the heart actually runs two circuits at exactly the same time.
It's doing two things at once.
Yes. It is literally two separate pumps fused together, sitting side by side, working in tandem.
See, here's where it gets really interesting for me. Because looking at it as two separate pumps makes the whole anatomical design suddenly make sense.
It clears up a lot of the mystery.
Yeah, because the right side of the heart is essentially receiving the blood that is returning from the body. This is blood that has already dropped off its oxygen to your cells and is now carrying a waste product, carbon dioxide.
Precisely. The right side takes that oxygen-depleted blood and pumps it a very short distance, literally just next door, to your lungs.
Just a quick trip.
Right. In the lungs, the blood dumps the carbon dioxide, which is the gas you exhale, and picks up a fresh new load of oxygen from the air you just breathed in.
I was actually trying to picture this division of labor, and I came up with an analogy.
Oh, let's hear it.
So think of the right side of your heart like a little local delivery van.
Okay, I like that.
It just does these quick, short trips back and forth to the local warehouse, the lungs, to drop off trash and pick up new supplies.
Yeah.
It doesn't need a massive engine for that.
That's exactly it. It's a low-pressure job. But then that freshly oxygenated blood travels back from the lungs to the heart, and this time it enters the left side.
And that's a whole different ballgame.
A vastly different job. It has to take that fresh blood and pump it out with enough force to push it all the way to your entire body.
Right.
Up against gravity to your brain, all the way down to your feet and back again.
So if the right side is the local delivery van, the left side is like a massive long-haul semi-truck.
Oh, absolutely.
It has to drive those supplies clear across the country to every distant zip code in your body. And that perfectly explains the physical structure of the organ.
Because of the muscle mass.
Right? The left side of the heart is physically much more muscular and thick than the right side. It literally built a much bigger engine to push fluid through 100,000 kilometers of pipe.
The physical demands on that left ventricle, that left lower chamber, are immense. And then, the body uses up the oxygen that the semi-truck delivers. The now depleted blood travels back to the right side of the heart, and the whole double loop begins again.
But if you have this heavy-duty semi-truck pushing fluid that hard, how does it not just, wash backward the second the muscle relaxes?
The recoil, yeah.
Right. Like, what is the actual mechanical sequence of the beat?
So to understand the beat, you have to look at the internal architecture. The heart is divided into 4 rooms or chambers, 2 on the right pump, 2 on the left pump.
Okay, 4 rooms.
And sitting between these chambers are sets of one-way doors, which we call valves.
Valves, right.
A heartbeat is simply the highly coordinated squeeze of those muscular chambers driving the blood forward, combined with those doors instantly snapping shut behind the blood.
So it can't go back.
Exactly, to absolutely prevent it from sloshing backward into the chamber it just left.
Wow. So when I hear that classic sound, like when a doctor puts a stethoscope to your chest and you hear that famous lub-dub, lub-dub, I've gone my whole life assuming that was the acoustic sound of a muscle flexing, like a bicep tensing up.
And you are not alone. Most people assume it's the muscle, but it is purely mechanical.
Really?
Yes. That lub-dub sound is the acoustic slam of those one-way valves snapping shut in rapid sequence against the fluid.
That is mind-blowing.
Yeah, lub is the first set of doors slamming, dub is the second set. You are quite literally listening to a hydraulic machine locking its doors against the backward pressure of the blood.
So the lub-dub is literally just the plumbing system fighting gravity.
Basically, yes.
But muscles don't just flex on their own. They need an ignition switch. And this brings us to the electrical system, which is, this is where things get truly bizarre.
It is arguably the most elegant part of the entire organ. Tucked away right inside the muscular wall of the right side of the heart is a tiny, specialized cluster of cells. We call it the natural pacemaker.
The natural pacemaker, okay.
Its sole biological purpose is to spontaneously fire off a tiny electrical spark.
Just on its own.
Yes, that spark spreads rapidly across the heart muscle, and that wave of electricity is what commands the chambers to contract in exactly the right order at exactly the right millisecond.
Okay, wait. Let me push back on this for a second, just to make sure I am grasping the implications here. Are you saying my brain isn't actively telling my heart to beat right now?
What's fascinating here is exactly that. Your heart does not wait for conscious or even unconscious instructions from your brain to initiate a physical beat.
That is wild.
It sets its own autonomous pace. Now, your brain and your nervous system can send chemical signals to the pacemaker to say, hey, we are running for our lives, speed the assembly line up.
Or, we're sleeping.
Right, we are deep in sleep, slow things down. But the fundamental spark, the actual ignition of the engine, is generated by the heart itself, completely independent of the brain.
That explains so much about medical emergencies. Like, that is why, if you've ever seen footage or read about transplant surgeries, a human heart can literally be removed from a body and, for a brief time, just keep right on beating in a tray as long as it has oxygen.
Exactly.
Because it's providing its own spark plug.
It has its own isolated power grid.
Yeah.
And understanding that grid is exactly how medical technology was able to invent artificial pacemakers.
Oh, of course.
Yeah. If that tiny natural cluster of cells, that ignition switch, starts to falter, or if the wiring gets frayed as we age, a surgeon can implant a small artificial battery that simply takes over the job.
It just mimics the spark.
Precisely. It sends that exact same regular autonomous electrical spark into the muscle to keep the rhythm going perfectly.
So we have this brilliant autonomous electrical grid setting the pace, and these mechanical doors snapping shut to push the fluid forward. But let's look at the cargo that is actually moving along these highways.
The blood itself.
Yeah, because we talk about blood like it's just a simple red liquid, right? Like water with food coloring in it.
Oh, it is far more complex than that. Blood is actually a living tissue.
A tissue.
Yes. And it has several highly distinct jobs happening simultaneously. To start with, all of this living cellular cargo is suspended and carried in a straw-colored fluid called plasma.
Plasma, okay.
If you were to put a vial of blood in a centrifuge and spin all the heavy cells down to the bottom, you'd be left with this yellowish, watery liquid on top. That plasma is the river itself.
And floating in that river, you have the cargo ships.
Mm-hmm.
The most famous, of course, being the red blood cells.
The red blood cells are the dedicated oxygen ferries. They are packed with a highly specialized iron-rich protein called hemoglobin.
Hemoglobin, right. I remember that from science class.
As they pass through the lungs, that hemoglobin binds tightly to oxygen molecules. That iron-rich protein binding with oxygen is exactly what turns the blood that bright, deep red color.
That makes perfect sense. And riding right alongside them in the plasma, you have the white blood cells, which are essentially the internal security apparatus.
Yes, the immune defenders.
Right. They are a core part of your immune system, constantly patrolling the bloodstream, looking for invading bacteria, viruses, or even abnormal cells to attack and dismantle.
And finally, you have the platelets.
Ah, the platelets.
These aren't even full cells, actually. They are tiny, specialized fragments of cells, and their job is to act as the emergency structural repair crew.
How does that work?
If a blood vessel gets damaged, cut, or torn, structural proteins in the pipe wall are suddenly exposed to the flowing blood. The platelets instantly detect those proteins, rush to the site, stick to the walls and to each other, and form a physical plug, a clot, to stop the leak before you bleed out.
That's incredible. So you have the river of plasma, the red oxygen cargo ships, the white security guards, and the platelet repair crews. And they are all traveling on a very specific set of roads.
They sure are.
The plumbing itself is divided into three main types of vessels, right?
Yes, and their structures are dictated entirely by physics. The first are the arteries.
Okay, arteries.
Arteries always carry blood away from the heart. Because they are taking the direct, high-pressure physical blast from that heavy-duty left pump we talked about, arteries have to be built tough.
They need to handle the semi-truck pressure.
Exactly. They have thick, highly muscular, elastic walls that expand and contract to handle the sheer force of the fluid hitting them.
Which brings up a term everyone listening has heard 1,000 times: blood pressure.
Oh, yes.
When a doctor wraps that cuff around your arm and pumps it up, they aren't just taking like an abstract health reading. They are literally measuring the physical tension inside your own pipes in that exact moment.
That is literally what they're doing.
They are measuring the sheer physical force of the blood pushing outward against those thick artery walls as the heart pumps.
That is exactly what that number is. It's a measure of the tension in the system. So the arteries carry the high-pressure blood away. But as they get further from the heart, they branch out, getting smaller and smaller, until they turn into the second type of vessel capillaries.
The capillaries are, honestly, they're my favorite detail in all of this.
They are pretty amazing.
These vessels are so incredibly fine, so microscopic, that the blood cells actually have to pass through them in single file.
Like a tunnel.
Yeah. I was visualizing it like a massive national road network. The arteries coming off the heart are like massive, high-speed, concrete, multi-lane highways.
Sure.
But eventually, those highways have to take exits into towns, then neighborhoods, and finally down to tiny, single-lane dirt roads, the capillaries.
I love that analogy.
And it's on those microscopic, single-lane dirt roads that the actual hand-to-hand delivery of oxygen and nutrients to your individual muscle and organ cells takes place.
It's the perfect visual because the capillaries have incredibly thin walls, often just one cell thick, specifically so that oxygen and nutrients can easily slip through the wall into the surrounding tissue, and carbon dioxide can slip back in.
Just a quick swap.
Right. Once that molecular exchange happens, those tiny capillaries merge back together. They get wider and wider, turning into the third type of vessel veins.
And veins are the return trip.
Exactly. Veins are the low-pressure return pipes that bring the now depleted blood back to the right side of the heart, the local delivery van, to start the whole massive process over again.
So understanding this high-pressure plumbing network, and especially those sticky little repair platelets that form clots, is critical when we look at why this system breaks down.
This is the really important part.
Yeah, because when we talk about cardiovascular disease, we are talking about the world's leading cause of death. But I feel like most people deeply misunderstand what is actually failing.
How do you mean?
Well, we usually think of a heart attack as the engine itself just giving out, like a motor blowing a gasket.
And that is the most common misconception. It is almost never a problem with the motor itself. It is a problem with the plumbing.
The plumbing, okay?
Here is the mechanism. The heart muscle is working constantly. It never rests. Which means the heart itself needs a massive, continuous supply of its own oxygenated blood.
Right. It can't just run on fumes.
Exactly. And it doesn't just absorb oxygen from the blood sloshing around inside its internal chambers. It relies on its own private, dedicated set of arteries, called coronary arteries, which wrap around the outside surface of the heart like a crown.
So the engine needs its own fuel lines to keep pumping fuel to everything else.
Precisely. Now, over many years or decades, those vital coronary fuel lines can slowly start to narrow.
From what?
Fatty deposits, cholesterol, and cellular waste, which we collectively call plaques, gradually build up inside the inner walls of those specific arteries.
Just kind of lining the pipes?
Right. This slow, decades-long buildup process is a condition known as atherosclerosis.
So we have this gunk slowly turning a wide pipe into a very narrow pipe. But a heart attack is sudden. It happens in minutes. So the slow narrowing isn't what instantly kills you, right?
No, the narrowing just sets the stage for the catastrophe.
Okay, so what actually triggers it?
What happens is that the surface of one of these fatty plaques on the artery wall suddenly tears or ruptures.
Oh.
And when that inner lining tears, remember those platelets we talked about? The
Yeah.
emergency repair crew?
Oh, wow. Wait, the body senses the ruptured plaque as a damaged blood vessel? It thinks it's springing a leak.
Yes, you got it.
That is tragic.
It really is. The platelets detect the exposed proteins from the tear, and they instantly rush in to fix it. They do their evolutionary job perfectly. They clump together and form a rapid blood clot over the rupture.
But the pipe was already narrow.
Exactly. Because the artery was already severely narrowed by the plaque buildup, that sudden structural clot entirely blocks whatever small opening was left in the pipe.
It just plugs it completely.
Suddenly, in a matter of seconds, absolutely zero blood can flow past that point.
So what does this all mean? It means the repair crew actually causes the final blockage.
Sadly, yes.
And the patch of heart muscle downstream of that blocked pipe is instantly starved of oxygen. It is suffocating.
It is suffocating.
Yeah.
And if that physical clot isn't cleared by emergency doctors very, very quickly, that specific section of the heart muscle begins to permanently die.
That is terrifying.
And that is the literal definition of a heart attack. It is not the heart simply stopping out of nowhere. An electrical failure where the heart just stops beating is called cardiac arrest.
Oh, I see.
Yeah, a heart attack is a plumbing blockage that cuts off the heart's own personal supply lines, suffocating a section of the muscle while it desperately tries to keep working.
And it's worth noting that a stroke is basically the exact same mechanical plumbing failure,
A
right?
ruptured plaque and a sudden clot, yes.
But the blocked pipe happens to be feeding a section of the brain instead of the heart.
Correct. It is the exact same underlying disease process, just striking a different destination in the highway network.
Man, I know that talking about ruptured plaques and suffocation strokes sounds, well, it's terrifying.
It can be very scary to think about.
It feels like we are all just walking around with these fragile time bombs in our chests. But looking at it as a mechanical plumbing issue completely changed how I think about maintenance. It actually makes it incredibly empowering.
If we connect this to the bigger picture, empowerment is exactly what this knowledge provides.
Because we can do something about it.
Absolutely. It is true that some of your risk for cardiovascular disease comes down to age and genetics. You can't control who your parents are, and you can't stop the clock.
Right.
But a massive proportion of your risk is dictated by mechanical factors you completely control.
We're talking about the major lifestyle factors: high blood pressure, smoking, physical inactivity, poor diet.
The classics.
Yeah, when you just hear a doctor list those off, they sound like generic wellness tips. But when you understand the mechanics, you realize they're physical maintenance steps for the pipes.
It's pure engineering.
Right. Take smoking, for example. How does inhaling smoke actually cause a heart attack in a chest pipe?
It is entirely chemical and mechanical.
Okay.
The thousands of toxic chemicals in cigarette smoke enter your bloodstream and physically scar the delicate, slippery inner lining of your blood vessels.
They damage the walls?
Yes. They essentially create microscopic potholes and rough patches along the walls. Those rough patches are exactly where circulating cholesterol gets caught and begins to build those deadly plaques. Smoking destroys the Teflon coating of your highways.
So quitting smoking isn't just about your lungs. It's stopping the active destruction of your plumbing's nonstick surface.
Beautifully put.
And what about exercise? Why does going for a jog protect the heart?
Because it forces the system to adapt. When you exercise, your heart pumps harder, and your blood vessels are forced to dilate to widen to accommodate the increased blood flow.
It's like a workout for the pipes themselves.
Doing this regularly keeps the muscular walls of your arteries flexible, elastic, and strong. If you are entirely inactive, the vessels become stiff and rigid.
And I'm guessing rigid pipes aren't good,
No, rigid pipes under pressure are far more likely to sustain the micro tears that lead to plaque buildup.
which ties perfectly into blood pressure. If you have chronic high blood pressure, it's like running a garden hose at maximum blast 24 hours a day, 7 days a week.
It's so much unnecessary wear and tear.
Eventually, the rubber's going to get stressed, fray, and sustain damage.
Yeah.
Managing your blood pressure through diet, like, watching your sodium intake or through medication, is literally just turning the faucet down so the pipes don't blow out.
Exactly. And a balanced diet simply manages the amount of raw material like LDL cholesterol that is floating around in the plasma, looking for a pothole to get stuck in.
It's all connected.
The evidence in the medical community is overwhelming. Moving your body, not smoking, eating reasonably, and managing your blood pressure genuinely, measurably protects this mechanical system.
It honestly asks for very little in return for beating 100,000 times a day without complaint.
It really doesn't ask for much.
It's doing the most vital job in your entire body. And all it really asks is that we take it for a walk to keep the pipes flexible and eat a vegetable now and then so we don't clog the fuel lines.
When you view it as a machine, it's a very fair trade.
It really is. So just to wrap up our journey today, we've zoomed in on this fist-sized double pump engine. We've seen how the right side acts as the local van feeding the lungs, while the left side is a semi-truck powering the entire body.
A brilliant division of labor.
We explored its autonomous electrical grid that sparks every single beat without waiting for the brain's permission. We rode along a 100,000-kilometer network of muscular highways and microscopic dirt roads, carrying a living cellular cargo.
It's quite a trip.
And most importantly, we've seen how keeping those pipes flexible and clear of plaques is the ultimate key to maintaining the whole incredible system.
And as we sign off, I want to leave you with one final thought to mull over, building on what we discussed about that natural pacemaker.
Oh, I like this.
We talked about how the heart has its own independent electrical system, right? It sets its own pace. It doesn't wait for the brain to initiate the beat.
Right, the autonomous spark.
Which raises an absolutely fascinating question about the human experience. When you feel sudden, gripping anxiety or a massive rush of excitement or a moment of deep, profound calm, we usually assume those emotions originate entirely in our minds and our body just reacts.
Sure, brain first, body second.
But if this little engine in your chest is autonomously adjusting its pace to the physical chemistry of your body, independent of your brain's direct control, how much of what we consider to be our emotions is actually just our brain reacting to the autonomous speeding up or slowing down of that little electrical spark in our chest?
Oh, wow.
Are we feeling our thoughts, or are we simply feeling our pump?
Wow. Are we feeling our thoughts or are we feeling our pump? I am going to be thinking about the direction of that feedback loop all day. Thank you for joining us on this deep dive. The next time you happen to feel your pulse, maybe spare a quick thought of gratitude for the hardest working muscle you own. See you next time.